Welcome friends. In this session, we describe surface integrals of vector fields. Recall that in line integrals, the orientation of the curve we were integrating along could change the answer. The same thing will hold true with the surface integrals. So before we really get into doing surface integrals of vector fields, we first need to introduce the idea of an oriented surface. Oriented surfaces. We call a smooth surface S orientable or two-sided if it is possible to define a field n of unit vectors on S that varies continuously with position. Any patch or subportion of an orientable surface is orientable. Spheres and other smooth closed surfaces in space, smooth surfaces that enclose solids, are orientable. The surface can be thought of as to have two sides of which one is arbitrarily chosen, positive side, and the other the negative side. By convention, outer side is chosen as positive. We choose n on a closed surface to point outward. Once n has been chosen, we say that we have oriented the surface and call the surface together with its normal field an oriented surface. The vector n at any point is called the positive direction at that point. Example for non-orientable surface. There are non-orientable surfaces also. A well-known example of such a surface is the Mobius strip shown in figure 1. When a normal vector which is given at P0 is displayed continuously along the curve C in figure, the resulting normal vector upon returning to P0 is opposite to the original vector at P0. A model of a Mobius strip can be made by taking a long rectangular piece of paper, making a half twist and stitching the shorter sides together so that 2 points A and the 2 points B in figure coincide. Remarks. In the case of a closed surface, usually the outer side is taken as the positive side. In our discussion that follows, we denote the positive side of the surface by S. The unit normal at any point to the surface drawn in the positive side is denoted by n. Sometimes a two-sided surface S may be bounded by a simple closed curve C. Surface integrals of vector fields. Suppose S, the positive side of the surface, be divided into a number of elements of area delta Si. Let P of xyz be an arbitrary point in delta Si. We take n is equal to n of xyz be the unit normal outward vector drawn at the point P on delta Si. Then f of xyz dot n of xyz represent the component of f along the normal to S at P. Notation. To get a compact form, hereinafter we denote f of xyz dot n of xyz simply by f dot n, noting that the value of f dot n depends on the point we choose. Now, f dot n delta Si represent the total number of lines of force or total flex over the element area delta Si. Considering flex over all such elemental area, we form the sum sigma f of xyz dot n of xyz delta Si. Then the limit of this sum as each delta Si tends to 0 is defined as the surface integral of S over S and is denoted by double integral over S f dot ds. This is sometimes called the flex of f across S. Hence, double integral over S f dot ds is equal to limit delta Si tends to 0 sigma f dot n delta Si, where ds equal to ds of xyz is the vector valued function called the surface area differential given by ds equal to dy dz I plus dz dxj plus dx dyk. We note that ds equal to dsn, where ds is the elementary area of the surface S at the point P and n is the unit normal to the surface at that point. Hence, we have double integral S f dot ds is also denoted by double integral over S f dot n ds. Hence, double integral over S f dot n ds is equal to double integral over S f dot ds, which is equal to limit delta Si tends to 0 sigma f of xyz dot n delta Si. Special case. If f dot n is equal to phi of xyz, then double integral over S f dot n ds is equal to double integral over S phi of xyz ds. Remark: another type of surface integral is double integral over S f cross n ds. Evaluation of surface integrals. Method 1. Using double integrals. For evaluating surface integral, it is convenient to express them as double integrals taken over orthogonal projection of the surface S on one of the coordinate planes. But this is possible only if any line perpendicular to the coordinate plane chosen meets the surface S in not more than one point. If the surface does not satisfy this condition, then it may be subdivided into surfaces which satisfy this condition. Let R be the orthogonal projection of S on the xy plane. Let P of xyz be any point on S. If gamma, the acute angle which the outward normal n at P of xyz to the surface S makes with the z axis, then cos gamma ds is equal to dx dy, where ds is the elementary area of the surface S at the point P. Hence, ds is equal to dx dy by cos gamma, which is equal to dx dy by determinant n dot k, where k is the unit vector along z axis. Hence, double integral over S f dot n ds is equal to double integral over R f dot n dx dy by determinant n dot k, where R is the orthogonal projection of the surface S on the xy plane. Remark 1. Similarly, if we consider the projection of S on the yz plane, we have double integral over S f dot n ds is equal to double integral over R1 f dot n dy dz by determinant n dot I, where R1 is the projection of S on the yz plane. Remark 2. If we consider the projection along the xz plane, we have double integral S f dot n ds is equal to double integral over R2 f dot n dz dx by determinant n dot j, where R2 is the projection of S on zx plane. Method 2. Surface integral can also be evaluated using Gauss divergence theorem. Gauss divergence theorem will not be discussed in this session. Example 1. Evaluate double integral over S f dot n ds, where f is equal to yzi plus zxj plus xyk and S is the surface of the sphere x square plus y square plus z square equal to 1, which lies in the first octant. Solution. A vector normal at the point P of xyz on the surface S in the first octant is given by gradient of x square plus y square plus z square minus 1 is equal to 2xi plus 2yj plus 2zk. Thus, the unit normal at P of xyz of S is n is equal to 2xi plus 2yj plus 2zk by root of 2x whole square plus 2y whole square plus 2z whole square, which is equal to xi plus yj plus zk. Since x square plus y square plus z square equal to 1 on the surface S. Now, we note that double integral over S f dot n ds is equal to double integral over R f dot n dx dy by determinant n dot k, where R is the projection of S on the xy plane. Being the projection on the xy plane of the portion of the sphere x square plus y square plus z square equal to 4 in the first octant, the region R is bounded by x axis, y axis and the first quadrant of the circle x square plus y square equal to 1. Also, z is equal to 0 on R. We find f dot n is equal to yzi plus zxj plus xyk dot xi plus yj plus zk, which is equal to 3xyz, and n dot k is equal to xi plus yj plus zk dot k, which is equal to z. Since S lies in the first octant, determinant of n dot k is equal to z. Hence, double integral over S f dot n ds is equal to double integral over r 3xyz by z dx dy, which is equal to double integral over r 3xy dx dy. In polar coordinates, points x, y in the region R is given by x is equal to r cos theta, y is equal to r sin theta. 0 less than or equal to r less than or equal to 1. 0 less than or equal to theta less than or equal to pi by 2. Hence, double integral over s f dot n ds is equal to 3 into integral 0 to pi by 2 integral 0 to 1 r cos theta r sin theta r d theta dr, which is equal to 3 by 8 on simplification. Example 2. Evaluate double integral over s f dot n ds, where f is equal to z I minus x j minus 3y square z k, and s is the surface of the cylinder x square plus y square is equal to 4, included in the first octant between z is equal to 0 and z is equal to 3. Solution. A vector normal to x square plus y square equal to 4 is given by gradient x square plus y square minus 4 is equal to 2xi plus 2yj. Thus, the unit normal at any point xyz on S is given by n is equal to 2xi plus 2yj by root of 2x whole square plus 2y whole square, which is equal to 2xi plus 2yj by root of 4 into x square plus y square, which is equal to x by 2i plus y by 2j, since x square plus y square equal to 4. Now, project S on the zx plane and call the projection R. We bring your attention to note that in this case, we cannot take projection of S to the xy plane as the surface S is perpendicular to the xy plane. Then, double integral over S f dot n ds is equal to double integral over r f dot n dz dx by determinant n dot j. Here, f dot n is equal to 1 by 2 xy plus zx and n dot j is equal to 1 by 2 y. Therefore, double integral over s f dot n ds is equal to double integral over r f dot n dz dx by determinant n dot j, which is equal to integral z is equal to 0 to 3, integral x is equal to 0 to 2, xz plus xy by y dx dz, which is equal to integral z is equal to 0 to 3, integral x is equal to 0 to 2, xz by root of 4 minus x square plus x dx dz, since y is equal to square root of 4 minus x square on S, which is equal to integral 0 to 3 minus z square root of 4 minus x square plus x square by 2 over the limit x is equal to 0 to 2 dz, which is equal to integral 0 to 3 z plus 2 dz, which is equal to z square by 2 plus 2z over the limit 0 to 3, which is equal to 21 by 2. Example 3. Compute the surface integral of the normal component of f equal to x square I plus yxj plus zxk over the triangle with vertices 1, 0, 0, 0, 2, 0 and 0, 0, 3. Solution. The equation of the plane passing through 1, 0, 0, 0, 2, 0 and 0, 0, 3 is x minus 1, y minus 0, z minus 0, 0 minus 1, 2 minus 0, 0 minus 0, 0 minus 0, 0 minus 2, 3 minus 0, which is equal to 0. That is 2 into determinant x minus 1 z minus 1 0 plus 3 into x minus 1 y minus 1 2 equal to 0. That is, the equation of the plane is 6x plus 3y plus 2z is equal to 6, and a vector normal to it is given by gradient 6x plus 3y plus 2z minus 6 is equal to 6i plus 3j plus 2k. Thus, the unit normal at any point xy set on the triangle S is given by n is equal to 6i plus 3j plus 2k by square root of 6 square plus 3 square plus 2 square, which is equal to 6 by 7 I plus 3 by 7 j plus 2 by 7 k. Hence, f dot n is equal to 6 by 7 x square plus 3 by 7 yx plus 2 by 7 zx and n dot k is equal to 2 by 7. Therefore, double integral over S f dot n ds is equal to double integral over R f dot n dx dy by determinant n dot k, which is equal to integral 0 to 1 integral 0 to 2 minus 2x 7 by 2 into 6 by 7 x square plus 3 by 7 yx plus 2 by 7 zx dy dx, which is equal to integral 0 to 1 integral 0 to 2 minus 2x 3x square plus 3 by 2 yx plus zx dy dx. On S, we have z is equal to 3 minus 3x minus 3 by 2 y, so that zx is equal to 3x minus 3x square minus 3 by 2 yx. Therefore, double integral over S f dot n ds is equal to integral 0 to 1 integral 0 to 2 minus 2x 3x dy dx, which is equal to integral 0 to 1 3x into 2 minus 2x dx, which is equal to 3x square minus 2x cube over the limit 0 to 1, which is equal to 1. Example 4. Evaluate double integral over S f dot n ds over the surface of the tetrahedron with vertices 1 0 0, 0 2 0, 0 0 3, 0 0 0, where f is equal to x square I plus yxj plus zxk. Solution. We subdivide the surface tetrahedron into 4 surfaces. The triangle with vertices 1 0 0, 0 2 0 and 0 0 3. Triangle with vertices 1 0 0, 0 2 0 and 0 0 3. Triangle with vertices 1 0 0, 0 2 0 and 0 0 3. And triangle with vertices 1 0 0, 0 2 0 and 0 0 3. 1. We have already computed the integral over one surface in the last example. 2. Along the bottom face we have n is equal to minus k and hence f dot n is equal to minus zx. But since z is equal to 0, the integral over the bottom face is 0. 3. On the face at the left we have n is equal to minus j and hence f dot n is equal to minus yx, which is also 0 since y is equal to 0 there. 4. On the rear face in the yz plane n is equal to minus I and f dot n is equal to x square is equal to 0. It follows that there is only one non-zero contribution to the surface integral and hence double integral over S f dot n ds is equal to 1. Example 5. Evaluate double integral over S f dot n ds where f is equal to x plus y I plus xj plus zk and S is the surface of the cube bounded by the planes x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1, z is equal to 0, z is equal to 1. Solution. Since cube has 6 faces, the given surface of the cube bounded by the planes x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1, z is equal to 0, z is equal to 1 can be considered as the union of the 6 surfaces faces with S1, S2, S3, S4, S5 and S6 whose equations are x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1, z is equal to 0 and z is equal to 1 respectively. The normal vectors to each surface face is given by n1, n2, n3, n4, n5 and n6 etc. Now on S1, n1 is equal to minus I, x is equal to 0, therefore f is equal to yi plus zk and y varies from 0 to 1 and z varies from 0 to 1. Therefore, double integral over S1 f dot n1 ds is equal to minus integral 0 to 1 integral 0 to 1 y dy dz, which is equal to minus 1 by 2 on simplification. On S2, n2 is equal to I, x is equal to 1. Therefore, f is equal to 1 plus y I plus j plus zk and y varies from 0 to 1 and z varies from 0 to 1. Therefore, double integral over S2 f dot n2 ds is equal to integral 0 to 1 integral 0 to 1 1 plus y dy dz, which is equal to 3 by 2. On S3, n3 is equal to minus j, y is equal to 0. Therefore, f is equal to xi plus xj plus zk, and x varies from 0 to 1 and z varies from 0 to 1. Therefore, double integral over S3 f dot n3 ds is equal to minus integral 0 to 1 integral 0 to 1 x dx dz, which is equal to minus 1 by 2. On S4, n4 is equal to j, y is equal to 1. Therefore, f is equal to x plus 1 I plus xj plus zk, and x varies from 0 to 1 and z varies from 0 to 1. Therefore, double integral over S4 f dot n4 ds is equal to integral 0 to 1 integral 0 to 1 x dx dz is equal to 1 by 2. On S5, n5 is equal to minus k, z is equal to 0. Therefore, f is equal to x plus y I plus xj, and x varies from 0 to 1 and y varies from 0 to 1. Therefore, double integral over S5 f dot n5 ds is equal to integral 0 to 1 integral 0 to 1 0 dx dy, which is equal to 0. On S6, n6 is equal to k, z is equal to 1. Therefore, f is equal to x plus y I plus xj plus k, and x varies from 0 to 1 and y varies from 0 to 1. Therefore, double integral over S6 f dot n6 ds is equal to integral 0 to 1 integral 0 to 1 1 dx dy, which is equal to 1. Adding all the above, we have double integral over s f dot n ds is equal to minus 1 by 2 plus 3 by 2 plus minus 1 by 2 plus 1 by 2 plus 0 plus 1, which is equal to 2. In this session, we have defined surface integrals of vector fields. We have also discussed the idea of oriented surfaces. The method of finding surface integrals of vector fields have been described in this session. Before concluding the session, try the following assignments. Evaluate double integral over s f dot n ds, where f is equal to xi plus yj minus 2zk, and s is the surface of the sphere x square plus y square plus z square equal to a square above the xy plane. Evaluate double integral over s f dot n ds, where f is equal to zi plus xj minus y square zk, and s is the surface of the cylinder x square plus y square equal to 1 included in the first octant between planes z is equal to 0 and z is equal to 2. Evaluate double integral over s f dot n ds, where f is equal to 4xi minus 2y square j plus z square k, and S is the region bounded by x square plus y square equal to 4, z is equal to 0, z is equal to 3. Evaluate double integral over S f dot n ds, where f is equal to x plus y square I minus 2xj plus 2yzk, and S is the surface of the plane 2x plus y plus 2z is equal to 6 in the first octant. Here are some books for your reference. Murray R. Spiegel, Vector Analysis, Shom Publication Company, New York. N. Saran and S. N. Nigam, Introduction to Vector Analysis, Potishala Private Limit, Allahabad. Irvin Krasik, Advanced Engineering Mathematics, John Wiley and Sons, 1999. Shanti Narayan, A Textbook of Vector Calculus, S. Chand and Company, New Delhi. See you next time. Till then, goodbye.